Welcome back to The Explainer. Today we're diving into something pretty intense, a purely clinical, physics-based reconstruction of an absolutely unthinkable event, the hypothetical failure of the Three Gorges Dam. We're going to keep the emotion completely out of this, right? Just let the geography and the math do the talking. As you'll see, the sheer violence of these first 60 minutes really sets the stage for a long-term regional catastrophe. So let's just jump right in.
Before we get too deep, I really want to frame exactly what we're doing here today. Our guiding principle is just this. Let me walk you through the first 60 minutes. Not speculation, physics. We are strictly looking at the scientific realities of what would literally be an unprecedented event in human history.
Okay, to really grasp the scale of this potential disaster, we've got to start with this massive number, 39.3 trillion. The Three Gorges Reservoir sits at an elevation of 175 meters and holds back 39.3 cubic kilometers of water. That translates to an awe-inspiring 39.3 trillion liters. Honestly, it's a volume of water that's almost impossible to wrap your head around. But keep this number in the back of your mind, because it's the absolute physical engine for everything that follows.
Now you may be wondering, what could actually trigger a breach? Well, the variables range from natural to human-made. We're talking a magnitude 6.0 plus earthquake, a massive landslide generating a wave that just overtops the dam, maybe a military strike, or even just progressive structural failure over a long period. Just to be clear, we aren't here to validate any specific geopolitical theories or take sides on how it might happen. We're just taking one of these triggers as the starting point for our physics equation.
And that brings us to the timeline. We're going to break down this disaster using a ticking clock. Minute 0, the breach. By minute 30, the impact hits Yichang. And by minute 60, it's already approaching Jingzhou. The terrifyingly fast pace of this initial hour is entirely driven by this massive wall of water rapidly accelerating down the river valley.
Section 1. The initial breach, minute 0 to 5.
So concrete gravity dams don't just vanish all at once, right? What happens is a specific section gives way, and then the relentless force of all that water rapidly widens the opening. To understand the mechanics of that first surge, think about the 110-meter height difference between the reservoir surface and the river below. Engineers call this the head. That extreme elevation literally pushes billions of liters of water through the breach. When you factor in friction in the geometry of the valley, this water blasts out, violently accelerating to initial speeds of 70 to 100 kilometers per hour. The sound alone would be deafening tens of kilometers away, and the ground itself would violently shake.
Section 2. The wall of water. Minute 5 to 30.
As this initial wavefront leaves the immediate dam site and barrels down the canyon, the human scale of that speed becomes pretty terrifying. Yichang is a major city of 4 million people, located just 40 kilometers downstream. At those speeds, the flood reaches them in roughly 30 minutes. If we compare this to the catastrophic 1975 Banzhou dam failure, where the waters took hours to inundate major populations, this is completely different. Here, even with instantaneous detection, 30 minutes of warning for 4 million people, well, that isn't an evacuation. It's just a pure, frantic scramble for survival.
But here's the thing, it's not just a wave of clean water coming at them. This wave is carrying massive chunks of concrete from the dam itself, thick, heavy sediment from the reservoir floor, uprooted rocks, soil, and the twisted wreckage of literally all the infrastructure it just consumed upstream. So what hits first isn't just water, it's a highly destructive solid wall of mass and debris that strikes long before the actual flooding peaks.
The absolutely crucial concept to grasp here is lateral water loading. That's the horizontal force exerted by water pushing against a structure. Essentially, almost no buildings in a typical city are engineered to withstand this massive lateral force. What that means is this super-fast, debris-laden wave will systematically shear right off its foundation or just completely destroy almost everything in its direct path.
Section 3. The expanding flood, minute 30 to 60.
Now, as the wave blasts past Yichang, the local geography of the river valley totally changes the nature of this disaster. Back in the confined gorge, you have a 1.1 kilometer wide, high-speed torrent that is perfectly focused, almost like a laser beam. But as it hits the Zhenghan Plain, the terrain suddenly just flattens out. The wave slows down, sure, but it spreads out, expanding tens of kilometers wide, completely blanketing vast stretches of agricultural land, villages, and infrastructure under meters of thick, muddy water. Of course, the Chinese government does have contingency plans in place. They have these massive flood diversion areas where water would be intentionally channeled to relieve pressure.
But let's do a reality check here. Even with those designated zones actively working, official estimates state it would take a full 48 hours, 2 whole days, for the water arriving at the city of Shashi, 340 kilometers away, to meaningfully drop in level. And remember, Shashi is less than a quarter of the way to the coast at Shanghai.
Section 4. The energy of the event. Quantifying the catastrophe. Let's pause our ticking clock for just a second to clinically examine the sheer physics at play, because quantifying this catastrophe reveals numbers that are absolutely fascinating and honestly highly instructive. The basic physics math is pretty simple. E equals mgh, mass times gravity times height. If you take 39.3 billion tons of water, multiply it by the force of gravity, and multiply that by the 120-meter average elevation drop to the plains, well, you get an incredible 46 terajoules of potential energy. To put that 46 terajoules into perspective, we can actually compare it directly to the Hiroshima atomic bomb. The bomb was roughly 15 kilotons of TNT, releasing its energy in mere microseconds over a very localized area. The dam break? That equals about 11 kilotons of TNT. The total energy output is literally in the exact same order of magnitude. The stark difference is just the mechanism of destruction. Instead of an instantaneous flash and blast, it's a sustained, grinding release of energy over hours, stretching across hundreds of kilometers.
Section 5. Downstream progression. The long-term regional impact.
Okay, we are now transitioning out of that frantic, fast-paced 60-minute scramble and entering into a slow-moving, sustained catastrophe that would quite literally reshape the entire region over days and weeks. If we map out the geographic progression, Yichang gets hit in just 30 minutes. But Wuhan, 700 kilometers downriver, gets hit in hours to a day. Nanjing, that takes days. By the time it finally reaches Shanghai, 1,600 kilometers away, that high-speed wall of water has degraded into a massive prolonged inundation that lasts for days or even weeks. And all of that is heavily compounded by the tidal effects pushing back at the Delta estuary.
And this single number is exactly why we're studying this scenario so closely today. 400 million. That is the total population living along the Yangtze Plain between the dam and the sea. Think about that for a second. Every major transportation corridor and almost every major city in this massive economic zone is intricately tied to that river valley.
Now, obviously, not all 400 million of those people are in the direct path of the high-speed floodwaters, but the long-term regional impacts are staggering. We're looking at catastrophic infrastructure destruction, widespread water contamination, and severely disrupted global and domestic supply chains. Not to mention unprecedented mass displacement. If we compare this potential disaster to other historical events, like the catastrophic 1931 Central China floods, these sustained indirect impacts would easily dwarf it. We are looking at the largest exposure of any single disaster event in human history.
Section 6. Consequences versus probability. The honest take.
All right, I want to bring some careful balance back to our narrative and give you the honest take on the actual likelihood of this terrifying scenario. Let me reassure you right now, the probability of this actually happening is highly, highly unlikely. The Three Gorges Dam is massively over-engineered. It's built on solid granite bedrock, it's a super stable gravity dam, and it has been continuously, rigorously monitored for 20 years. But, and it's a big but, when the consequences of failure involve hundreds of millions of lives, even a 1 in a million probability demands serious, continuous scientific analysis.
Because the physics we've walked through today, the immense volume of water, the extreme elevation, the downstream geography, and that incredibly vast population density, none of these things are in dispute. They are just absolute physical facts. And those facts make the Three Gorges Dam undeniably the single most consequential structure on Earth. So, I'll leave you with this question to ponder. Does this physics-based reconstruction change your personal risk assessment? Think about that delicate balance between extreme consequence and low probability. Let me know your perspective in the comments below, and make sure you subscribe because in our next explainer, we'll be breaking down the downstream mortality geography in detail. Thanks so much for focusing in with me today, and I'll see you next time.